Okay, so in this video, we will solve this problem. This is actually a problem. You can see the boundary work for a constant volume process. So let's read the question at first. A rigid tank contains 5 air. So rigid tank contains air at 500 kPa and 150 degrees centigrade temperature. You look at this figure here. So this is actually the rigid tank. Initially the air is at 500 kPa, pressure at 150 degrees centigrade temperature. So what is happening here? You see heat is transferring from this container to the from this tank to the surroundings. So this system, it is actually releasing heat to the surroundings. And what is happening, like say after some times, the pressure reduces. So the pressure drop from 500 to 400 kPa, and the temperature also, you see, it's now 65. So initially it was 150 and now it becomes 65. What we need to do is we actually need to calculate the boundary work. I discussed the work and the heat transfer actually, so in my previous video. So here we actually need to calculate the boundary work done during this process. So if we start solving this problem, let's say look at this PV diagram here. So in this PV diagram, we just sketched what is happening. So this vertical axis, it is actually the pressure. If we go up, that means pressure is increasing. This is actually the volume. So volume is increasing this way. So what you can see, this is actually the state 1, this is state 2, or you can say stage 1, stage 2. So initially the pressure P1, it was 500, we said 1. This is the first step or the initial step, and then the pressure drops to 400. So it's say you see the pressure drops to 400, that's the stage 2. Temperature is changing here, 150 to 65, but it is PV diagram. So in this case, what we can see, guys, there's no information here regarding the volume, but what you know from this question, you can see this is a rigid tank. So rigid tank means, the volume is not changing here, it has a constant volume. So rigid means, it has constant volume, and actually the volume change, that means the dV, this is equal to 0, and that's actually reflects in this curve. You can see this is point A, this is 1, this is 2. So in this 2 point, you can see it's just the pressure drop. Okay, nothing happening, the volume is not changing here. So the volume here and the volume here, you can see this is the same. So that means no change of volume. And what we can see, it is from here, it is a rigid tank. So the boundary work, actually we know from the formula we discussed, the boundary work, it is actually we can write W, it is equal 1 to 2, that means the initial process and the end process, the pressure, and dV. Here actually this dV, it is equal 0. So that means it will be kind of 1 to 2 pressure into 0. So that means it will be 0. So the work done by the boundary, the work done, the boundary work done during this process, it is actually 0. No work is happening here. It is expected because we said it is a rigid tank. The rigid tank means the volume is not changing, it's constant. So one important thing now I'm going to tell you is actually we can say this is a problem which is constant volume process, and you can see the title, it is constant volume process. So any problem, actually any problem which is constant volume process, then the boundary work, it should be always 0. If it is a constant volume process, if the volume is not changing, so we know the formula is actually this. So if the volume is not changing, if it is constant, then actually the boundary work, it should be 0. And you can check the PV diagram, and you can see actually this is from the PV diagram, the area under the process curve, it is it is always 0. So the main theme from this constant volume process is the boundary work, it will be always 0. So yeah, I think that's it.